All right, so I've already talked to all you guys, but I am Pieter Тодd, and I am known for sometimes doing work on Bitcoin Core. Just enough work on Bitcoin Core that Craig Wright went and sued me along with all the other devs, so I guess I can say I'm a real dev. But other than that, I've also worked on open timestamps as well as like analysis systems, and well, that's where all this comes from. I was asked almost a year ago now to do a paper on L2 systems, and while the paper is, almost done, it'll be done soon, I can at least go talk to you about my findings. So, what makes an L2 an L2? Interesting question, actually. Do you guys think like liquids in L2? Lightning? What about Ethereum? Is Ethereum an L2? All right, well, if we're going to have an L2, we really should have an L1. And what I like to go and define an L1 as, of course, the first layer. But the spirit of this is really you're doing transactions with passive security. You're using some kind of consensus mechanism where once you create a transaction and you send it, the rest is kind of up to the system. Of course, Bitcoin itself is an example because miners have proof of work. They go do this hashing stuff and they build on the security blocks to create a consensus. And once you've paid your transaction fee and managed to convince a miner to get a transaction of yours into a block, you can just go walk away and that's that. Now, systems that work on top of this, such as RGB, they're also really, I think, spiritually L1s. You kind of call them like L1.5 or something, because while they may achieve better scaling than L1, ultimately the security model is still the passive security. My own open timestamps is another example, and it may not be transacting, but the security model is Bitcoin miners do everything for you, and that's that. And merge mining, again, I think is another example of an L1. Now, I'll point out, I don't think merge mining is a very good idea, but the security model at least is an L1. So, L2s, well, from the point of view of scaling, they tend to use some kind of like conglomeration where one transaction on chain represents many different transactions off chain. But the security model, the key thing about an L2 is that the security model tends to be something reactive in some way, or at least something kind of clever around incentives. And now, ironically, my first example almost doesn't fit this, which is check locked on verified payment channels. And if you're familiar with the history of Lightning, you may know what these are. And they're just one of many examples of payment channels. But the key thing to understand there is they're about taking one transaction to go set up a channel, put money into a 2 of 2 multisig. And then the security model is really you're giving the other party an option to take more and more money out. Right? I have a Bitcoin with you shared. Now I go give you half of that, and maybe 3/4 of that, and so on and so forth. And at every moment, it is in your incentive to take the maximum amount, which is the only amount that you really owe me. Now, is that really reactive security? Well, it's almost a little below L2 in that sense. But the moment you add Lightning, where there's now a step where potentially the money can flow in the other direction, that's clearly reactive. Now again, a recap, how does Lightning work? Well, with our payment channel, what if I want the money to flow in the other direction? Well, I can invalidate one of my prior states by giving you the ability to take all my money if I give you the ability to go and give me the ability to go take all the money if I try to go and mine a transaction where less of it flows in whatever direction. So you're reacting to the person doing the wrong thing by using a revoked transaction and punishing them. And ARC is something kind of like that too, and I'll get into more about ARC later. But I think the key thing we want to go say is really, while the nuances of L2s can be a little fuzzy and there could be different types, what we really want out of them is we want either unilateral withdrawal, that's always the best case, or to prevent the counterparty from committing fraud. And now unilateral withdrawal is easy enough to understand. Again, in Lightning, you can always close the channel by publishing the commitment, or at least the latest non-revoked commitment. and that takes the pot of money and splits it up amongst its rightful owners. But preventing the counterparty from benefiting from fraud, that's a little more subtle. So in Lightning, you actually see this in HTLCs. Now, recall, with an HTLC, it's a hash time-locked contract. Basically, it's a way of saying to a counterparty, you can get some money if you go prove knowledge of a message that hashes some digest. But what happens with an HTLC if you're trying to send like 1 Satoshi? You know, 1 Satoshi is such a tiny amount that you can't really represent it on chain. I mean, first of all, you can't have an output of 1 Satoshi with the dust rule. It's just invalid. Now, to be clear, it's invalid consensus-wise, but you know, nodes will reject outputs below the dust rule. And secondly, more importantly, I think, it just doesn't make any sense. Like, why would you put all these bytes on chain to try to get 1 Satoshi? Like, you're going to lose money. In fact, you know, frankly, Lightning doesn't do this properly because even a dust level HTLC is really worthless. But, you know, ignore that part. The important thing is that you can still prevent the counterparty from benefiting from fraud, because in Lightning, very small HTLCs get added to the fee. And the economics of this is that no one is going to close a channel to try to go steal an HTLC from someone. Like, it costs more in transaction fees. It doesn't make any sense to do it. Now, there are edge cases here where, like, if I have, 1,000 HTLCs in flight at once, maybe the economics work differently. But, that's a mistake in Lightning. It's not the spirit of what Lightning should be. So, what are some things that are not L2 systems? Well, I mentioned Liquid earlier, and I'm going to say it's not an L2 system because there's no unilateral withdrawal. And within the system, there is no mechanism to punish fraud. Now, certainly you could say it's an L2 because there's a way to punish fraud. It's called the legal system. But in Bitcoin, we don't like to use the legal system. So in the context of Bitcoin, yeah, Liquid is not an L2. It's a very fancy bank. Very nicely audited bank, but still a bank. Cashew, it's the same category as Liquid. While the accounting layer is different, ultimately, it's a bank. There's some guy with your money. You can ask the guy nicely to give you your money back, but ultimately there's nothing within the system that prevents him from taking it. In state chains is interesting. I'm not going to go into exactly how the hell state chains works, but roughly speaking, you could say it's almost like you had a Liquid where it had this magical property that provided your counterparty was being honest and then walked away from the system, they couldn't steal your money. The catch is that's not good enough, because if they're dishonest and then they actively interact with you, they can steal your money. Now, legally, this is an important distinction, because often in legal systems, the cops can go bust into your server farm and they can take everything, but they can't do anything further. Right? All they're allowed to do is turn off the computers and take the evidence. So in state chains, in that kind of situation, you're still more protected than the alternative, something like Liquid, where if they bust into every Liquid functionary at once, or at least enough of a majority of one, they absolutely can take the coins. In state chains, it's a bit more subtle, but I still don't think it meets the threshold to be an L2 system. So, covenants. Now we're talking about background. Now, if you want to do an L2 system that's more complex than Lightning, what's interesting is they all seem to want covenants. So what the hell is a covenant? Well, there's a bunch of different types, but roughly speaking, you can say a covenant is a way of creating a restriction on how a transaction can be spent. That's more interesting than just only that pub key can spend it. Because if it was only if checksig qualifies as covenant, everything's covenant, which is kind of useless. But if you limit it a little more, then you get something interesting. And pre-signed transactions, they're kind of covenants. And Lightning already uses these. Lightning uses these for various reasons in how HTLCs work. Because in an HTLC, you want the ability to go revoke the HTLC. And long story short is, to make this actually work, you need an HTLC output to be only spendable in a certain way. Well, how do we achieve that? Well, the two parties in a Lightning channel, they create a covenant by signing a transaction collectively that can only spend that HTLC in a certain way. And provided that no other transaction exists, the only way to spend that transaction is through that pre-signed transaction. Now, check template verify is probably where you first heard the term covenant. And that basically says, hey, does the spending transaction match this template? And the template is basically, are all the outputs what I expect? And is the input pub keys what I expect? Not the input hashes, because otherwise it'd be just a pre-signed transaction and not possible to actually create in advance. But it's kind of like saying the shape of how this is spent is predefined. Ccache any prev out is weird, basically because you can play really crazy math games apparently to go create covenants. I honestly couldn't tell you the details on how the hell this works, but it's sort of more a cautionary tale of if you give people the ability to go do things, they can go push it in remarkable ways with crazy math. Opcat is definitely a covenant, especially in conjunction with other things. And I'll give you an example of how it's a covenant exactly. But basically, if you can go build up a transaction on your stack, you can go check it against what's out there. And finally, you get a whole pile of other things that are really like covenants for particular use cases. Gleb actually came up with one of them. I think he called it Opovict or something or another. But he has a paper on this. But I'll cover that in a bit. And I also need to go talk about mempools. Because as it turns out, if you want to do L2 systems, including Lightning, current mempool policies are kind of a mess for what you actually need. And there's a whole lot of different attacks that people have found in the process and different things about this. One example that got a bunch of press was something called replacement cycling. And it's interesting because it's kind of like, it's not something you would expect to be possible, but long story short is, if you and I, maybe not even necessarily you and I, like even worse case in certain cases, but long story short is like, I can use replacement to get your transaction entirely out of mempools against your will. And that's even though you end up in a state where the transaction is still valid, it's just no one actually has a copy of it. And you do this by basically taking a transaction and replacing it with another one, then doing like one more replacement to kind of get back to another state where none of the outputs are spent. Well, what's the relevance of this? Well, again, let's talk about Lightning. Lightning is all these cases where like you need a transaction to get mined by a certain deadline. If someone does a replacement cycling attack on you and you don't notice it, you can end up missing that deadline because your transaction wasn't actually in miners' mempools. Now, I actually proposed a solution to this called op-expire, which solves the attack by saying, well, unless something happens by a certain time, like your ability to go and do something is gone. Well, why is that relevant? Well, replacement cycling is relevant to things like HTLCs, where you have some output, and if you can somehow delay that output being put on the chain, you can potentially go steal by violating a timeout. Well, if the timeouts are strict, so it's like you can't do anything after this point, you fix that problem. Obviously, I'm speaking kind of high level here, but you can go read more on the mailing list, but the details there. Transaction pinning is like another interesting class of attacks where where it why it comes out is basically, again, let's go back to the Lightning example. Lightning has deadlines. If I can prevent you from paying a high enough fee to get your transaction mined by a certain deadline, you might miss that deadline. Right? What might that look like? Well, Lightning, the commitment transaction, which both parties sign, if that fee is too low and I prevent that transaction from getting mined, one way that I could go screw the other guy over is really simple. I could just go and say, why don't I just go wait like 6 months until they give up? Like, it sounds stupid, but waiting 6 months until they give up, that's a reasonable attack. Like against a lot of people who might have $100 in their Lightning wallets, like they might go give up on $100 and then I can go take their money later. And well, there's a bunch of different ways to go fix transaction pinning, and they're all based around like games with replace by fee. And I'll mention that in a second. Fee payment in general is kind of a complex topic. Again, going back to Lightning, why is fee payment hard? Well, because we want pre-signed transactions. Pre-signed transactions, what fee should it pay? Ideally, the fee should be 0. We should be magically able to like somehow convince miners to go mine it. And that gets to out-of-band fee payment. If you notice on mempool.space, these days you can actually go to mempool.space and with a Lightning payment, go and get your transaction mined earlier. But that's bad, because like only half the miners are set up to do this. If you're a little Joe Blow like trying to do solo mining, you can't earn money from this. So that's really problematic. And child pays for parent is sort of the other category where you say, well, why don't we have the child transaction pay for the parent? And then that gets things like anchor outputs and whatnot, and it's a whole fractal of mess there. Replaced by fee rate is one of my things, which is meant to go solve transaction pinning by saying, I should point out like a big class of transaction pinning. It sounds kind of stupid, but I'll give you this analogy. Suppose you go to a cattle auction, and you rock up there in your big fake Texan hat, and you go and loudly tell everyone, I want to go buy 10,000 cattle for $1 each. And I'm pretty sure a cow is worth more than $1, so you're going to get laughed out of the room. But now suppose you go do a new bid. You're going to go buy 10 cows for, say 5 cows for $500 each. Right? $2,500. That looks pretty good. 500, that might be a reasonable price. Well, the way Bitcoin Core works with transaction replacement is your second bid would get rejected because the amount was less. And that means if the other guy can make a really big transaction spending your output, or fool you into making a big transaction spending your output at a low fee rate, your transaction is just stuck. Now, replaced by fee rate says, well, why don't we just compare the fee rates? Surely if you pay enough money per byte, it's worth mining. Well, it turns out that's complex because of free relay DOS attacks. You can have things where if you take a really big transaction, replace it with a small one, are you not paying for all the bandwidth you used? And because the difference between biggest and smallest transaction in Bitcoin, make sure the screensaver doesn't hit. Because the biggest smallest transaction in Bitcoin is like a 4,001 ratio, you could potentially use 4,000 times more bandwidth than you consume. Although, as it turns out, that's not really a true statement because we're already vulnerable to DOS attacks that way. You can always go use up bandwidth on the Bitcoin network by spending transactions all kinds of ways. So, arguably that's not a problem. And finally, the one bit of hope in this whole list for something we've actually fixed is full RBF. Remember what I said about transaction pinning? Well, the dumbest possible way of doing transaction pinning is to broadcast a transaction with the replacement flag off, right? Because it used to be, miners would just reject the next transaction. It didn't matter how much money it paid. They would just look at whatever the first one came and reject the second one. Well, that was stupid. So after 11 years, I finally convinced Bitcoin Core to enable replacement on all transactions by default. Miners were already doing this for, at least a year in large numbers, and more recently, for at least 6 months or so, because of weird ordinal auction protocols. Long story short is if you do replacement on every transaction, you earn a couple $1,000s more per block. Obviously, they're going to do that, but anyway, at least for that thing, we fixed that. So now that we've detoured into the madness of mempools, why the heck do we want better L2 systems than Lightning anyway? I mean, how many of you guys have actually used a Lightning wallet? Well, show of hands. All right, at least one guy. Come on, you've used one.
Yeah.
All right, you devs, you've got fine arts bullshit degrees and MBA or something, not our real comp sci degrees, but you're the one with actual Lightning experience. So you guys got to go do better on this. But maybe why you're not using Lightning is because it just doesn't work properly. I mean, everyone knows that Lightning has failed, right? Now, seriously, one of the big claims of Lightning has failed is that, well, Lightning channel needs a UTXO. How many possible UTXOs could there be out there? Well, it's not good. It's not that bad. Basically speaking, if 90% of the Bitcoin block space was used to open Lightning channels, you could open 1 billion of them in a year. Now, Is that enough? Well, I mean, one way to measure it is ask how many people in the world own smartphones. Apparently that number is like 4 or 5 billion. It's not that many. And like, how likely is it really that we're going to get Bitcoin adoption to the point where like everyone in the world with smartphone actually uses Bitcoin? I don't know. It might take a while. On the other hand, if you're a real bull and like assume Bitcoin's going to grow to, you know, $1 trillion per Bitcoin, that's potentially a real issue there. And you can potentially do better by having systems that share many users on one UTXO. How would you do that? Well, with covenants, of course. But, you know, that's potentially like the motivation there. Now, liquidity is an interesting topic where, of course, in a Lightning channel, you need funds associated with the channel. And especially from the point of view of a user, it's very annoying if you want to receive money from someone you don't have incoming capacity. And there are better L2 systems, or at least different L2 systems in Lightning that potentially fix this liquidity issue by being able to create UTXOs without actually creating UTXOs. And finally, the last one is a lot of people don't like Lightning because of interactivity requirements. Now, personally, I think maybe this is a bit overblown, but certainly it is the case in theory. If you have a Lightning channel with someone, if you don't have at least some third party like a watchtower watching it, they could steal your money by just broadcasting a revoked commitment transaction. Also, if you, on your side, broadcast the wrong commitment transaction, they can just take your money. So people have proposed systems that try to go fix this, but you know, that's a complex topic in and of itself. Speaking of, well, one of these classes of systems is called L2, which is a terrible, terrible, terrible name. It obviously was come up with people who don't give presentations. It's fine written down, but yeah, I'm going to go call it its much better name, LN symmetry. So, what is LN symmetry? Well, LN symmetry uses this new sighash flag, sighash any prev out, to basically say that when you close a Lightning channel, what you're doing is saying, all right, I have these funds. I'm going to propose a new state. You can propose a later state if you have one. And if you do, well, we'll negotiate, right? The later state will replace the earlier state. And every state in a Lightning channel has a number attached to it. So basically, if you figure out what's the latest state either side has, you'll get to the latest state of the channel. Now, normal Lightning, the way it works is I propose a state. If it's not the right one, the other guy can go take all the money because it's a revoked state. But in LN symmetry, it's a bit more friendly. Well, how do you actually do this? I honestly couldn't tell you exactly how off the top of my head, but long story short is you need a way of signing an output in such a way that the exact transaction ID doesn't matter. And sighash any prev out does this by saying, rather than signing which exact output we're going to spend, we're going to assign essentially what address of output we're going to spend. And that works with LN symmetry because one signature can be used for different versions of an output. So, channel factories. And, you know, I got to point out, LN symmetry, it just fixes that last bit, maybe, the interactivity. What if we want to improve scaling? Well, going back to our first problem, one Lightning channel, one UTXO. What if we somehow did better by creating more than one Lightning channel with one UTXO? Well, it turns out a very simple way to go do this is with a pre-signed transaction. Right? Like, let's suppose there's 3 of us and we all want to have Lightning channels with each other. What we could actually do is create an output that's signed by all 3 of us, and then create another transaction that we've pre-signed that takes that output and splits it into 3 different Lightning channels. And if it's now split into 3 different Lightning channels, if you need to go on chain, and you need your Lightning channel to go on chain, well, you broadcast the first transaction, that gets mined, and then you can broadcast the second one for your commitment. Basically, you're saying, like, I could go actually create these channels on chain, but I don't want to yet. But the interesting thing is, from Lightning's point of view, it doesn't matter that the actual outpoint of a Lightning channel exists or not. All that you need is the ability to make it exist. Because if you're ever in a position where you need to broadcast the commitment transaction and go on chain, so long as you can make that output exist, you can broadcast the commitment transaction. Now, why would you want to go do this? Well, again, we have 3 people who create channels. Let's suppose at some point we all mutually agree, all right, that was cool, let's close the channels. Provided that the original output is spendable by us, and it will be because it's multisig, we can just negotiate amongst ourselves, all right, what transaction should we sign to close the channel? And that transaction could be a lot smaller than actually going through the whole on-chain process. Now, of course, with 3, this isn't much, much reason to do this, but like rather than 3, if it's 1,000, maybe there is. And that gets you to advanced channel factories, which is really saying, well, what happens if we want like 1,000 people sharing an output? How the hell do we actually do this? Well, one way is to use trees. And there's a lot of different variants of this idea. But essentially, all this stuff boils down to, rather than creating all these channels in one go, we can have a tree of transactions that create whatever channels need to be put on chain. And for the people who do not want to go on chain, they can still negotiate amongst themselves to go and sign more efficient transactions. Now, because this can work as kind of a binary tree-like thing, the cost to put a channel on chain for at least one channel is roughly speaking like log 2n of how many people you're in there, which isn't great, but it's not that bad. Although it's very interesting that if like the first guy goes on chain, and then the next guy does, and so on, every time another person goes on chain, you reduce the cost for everyone else because more of these outputs are already there. And let's say everyone wants to go on chain. Well, curiously, your cost is roughly twice as much as it would have been if you just had one big transaction, right? Because it's a tree. If you sum a tree where like every level is half, that's roughly speaking 2n. I mean, if it's a true tree, it is 2n. But including overheads and transactions, it's roughly speaking 2n-ish. It's not that bad. It's not great, but it's not that bad. So, these kinds of things aren't that inefficient. They're not that great. But of course, once you go down this rabbit hole, you then start thinking, well, what if we have like a way to like add funds and remove funds? Like maybe we'll have some special tree opcodes where like you can evict a transaction, put it in, and there's a lot of complexity there. And I'm not going to go talk about that in 30, 40 minutes, but just know these ideas are out there. So, if you have a tree of transactions, I mean, couldn't you kind of say that these UTXOs are virtual? Well, Arc takes this to the extreme and says, rather than like only using this technique to open Lightning channels, what if we use this technique to trade UTXOs? And the way Arc basically works is you have a central party who collects requests for UTXOs. All right, they have a bunch of money, and they want to create an output that can be split into a whole bunch of different ways. Now, if that was all they did, obviously, like everyone in this room could ask the central party to create a virtual UTXO that could give them money by actually going on chain. But of course, that would be kind of useless, right? It doesn't actually do anything for you. It just means in the future, you can go pay more fees than you would have to get the UTXO created in the first place. But the trick is, with an Arc service provider, if there's a timeout on the length and time these virtual UTXOs exist, you can then set up a system where if none of these UTXOs actually go on chain, the ASP gets their money back, and they can get their money back very efficiently, all right? Because they just have to spend one output with like one signature. And if you know how Taproot works, I mean, Taproot fundamentally is about having a scheme where either you can spend your money with like a tree of different scripts or with a key. Well, this matches perfectly. Implemented with Taproot, the ASP would have a key where they can spend the money, or the money gets spent by splitting it up. And like the channel factories idea, the actual split would be done with different layers of transactions and so on. But the key thing is, how do you trade, how do you sell your virtual UTXO? Well, that comes down to this idea of a connector output. And basically it says, what if we had a way of saying that a transaction is only valid if another transaction exists? Or sorry, another transaction output exists. Well, if you can make that statement, the way you can sell a virtual UTXO can be, you take your UTXO, your would be completely valid if it went on chain UTXO, and sign a transaction, taking that money and giving it to the ASP. Yeah. We've got a lot over our roof. If it's not okay, we'll be extremely dead. We know that much. So, you have this idea of a connector, and you have your virtual UTXO, you're going to sell it to me, I'm the ASP. You sign a transaction that could be on chain, gives your money back, but that transaction, if it goes on chain, the only way it can exist is if a different arc round is created that gives you another virtual UTXO. All right? The only way I can go on chain, at least prematurely before the expiry, is by creating another round that gives you your money back. All right? So you're all good there. And once that new round, once that output actually exists on chain and is mined, you have your money. And I know I have my money because before you try to go spend it, I can just publish that transaction too and just take it. All right? That's kind of your security model there. It's like, you're in a position where I've already made the new money. If you try to take it, well, I'm going to get it too. Now, frankly, I think if someone really sat down with Arc and worked out the nuance of every possible state, Arc probably needs improvement to work properly. I think in here, I'm glossing over a lot of details here, and I've never seen a really, really good analysis on exactly how the hell Arc really would work, including the incentives for every single party at every single possible step. But the idea, I think, is reasonable. So what's the catch here? Well, this sounds all cool. You can create virtual UTXOs. Oh, and I should have actually mentioned, of course, if you have a virtual UTXO, just like the channel factories example, you can have a lightning channel off a virtual UTXO. So, that part's all well and cool. But the catch is, the Arc service provider, I have to front a lot of money. All right, because I have this 4-week expiry time. Well, if the 4 weeks are up, I can take your money. So you have a very strong incentive to go and either go on chain or get a new UTXO at the end of the 4 weeks. And you're not going to wait 4 weeks, minus an hour. You're going to wait 3 weeks, maybe 2 weeks. Well, now all the money in this round, I have to go front it 2 weeks in again, and then I have to go wait holding all this cash. I'm not sure Arc is actually going to be cheap, because frankly, the usual cost of money is, say, roughly 5% per year. Well, 5% per year, that could be your holding fee for owning money on Arc. Does economics that make sense? It depends. Certainly, if you're trying to have very small amounts, maybe this makes sense. Maybe 5% of a dollar doesn't really matter to you. But for large amounts, I don't think you'd want to go hold them on Arc. Paying transaction fees is likely to be better, but it depends. So, the last L2 system I'm covering in this hypothetical paper that certainly will be published soon is rollups. And rollups, I think, is an interesting category because rollups kind of comes from the crazy Ethereum world where everything's basically a scam. Yet rollups themselves aren't necessarily a scam. So, what the hell are they? Well, it's this idea that in particular with fancy zero-knowledge proofs, you could somehow have a transaction where it can only be spent if you prove that a different consensus system followed the rules. Well, how the hell would you do that? Well, first of all, what the hell is a ZK proof? Now, ZK stands for zero knowledge, which is not actually correct in this case, but The important thing about a ZK proof is it's kind of like a signature, but it more validates the execution of a computer program. So it's this magical signature that says, if you run this computer program with this data, it's going to return true. And that signature is small. Now, the smallness is where the zero knowledge comes in. For mathematical reasons, it turns out basically all the schemes that actually implement these zero knowledge proofs, they're zero knowledge in the sense that the signature doesn't reveal anything about the data. But for public systems like rollups, that part of it doesn't matter. And there's some optimizations where like they'll leak some data. So just know, ZK, it's kind of a misnomer. The important thing is that they're succinct proofs of a program execution. So if you had one of these, you could create an output where the thing you feed into it is you basically prove that this other thing, all the rules were followed, and this other thing could be a blockchain. So why do they call it a rollup? Because it's like we're taking all the state, all this off-chain state that did not go on the chain, and we're rolling it all up and taking all those different transactions and turning them to one little transaction. Catch is, like, there's a lot of different proposals here, and I'm not actually convinced that they really fall under the category of L2 systems. And the main reason is that a lot of these systems, they have a property that, let's suppose that the other guy doesn't actually do it properly. Right? Because, you know, these things involve state. Well, how does a Bitcoin chain know what state the rollup should be in? That's a very, very difficult problem. Probably in a lot of cases impossible, assuming you want the transactions to be off-chain. Now, if you want the transactions on Bitcoin, this is easy. If you just put the data on the Bitcoin chain, obviously, that can be your input to the program, and you're all good. But then we didn't get an efficiency improvement, right? Then it's more like an L1 system. If you want a true L2 system, we got to go do better. But if we try to go do better, now you have a central party running this roll-up, and they may not give your money back because you might not be in a position to go prove that they did something wrong. You know, you might not have the data. Well, one category of rollups is called optimistic rollups. It's this idea that you just assume it's correct and then you prove it isn't. But how do you prove it's not correct without the data? Turns out this is a very big problem, and I'm not going to talk much more about rollups because I'm just not convinced anyone's actually come up with a system that actually works. Of course, the flip side of all this is, let's assume that someone can implement a zero-knowledge proof on Bitcoin. The catch with that is you can do basically anything. And is that really what Bitcoiners want? I don't know. It isn't clearly useful. And then with all these systems, we have a class of problems I think I'm going to call the failure case scaling problem. Now, remember with a Lightning channel, the usual way that a Lightning channel is closed is by the two parties agreeing to close the channel, and they sign one transaction with, you know, two signatures, or with musig would be one signature. And that transaction gets mined, and that's that. Now, if a Lightning channel is closed in an uncooperative way, the size of the transaction that needs to be broadcast is a little bigger. And it needs to be a little bigger basically because of nuances of how Lightning works. Like, you need to give the other party a time to react, you know, which means you really need two transactions, et cetera, et cetera. But it's not that much bigger. I mean, it's, say, twice the size, 3 times the size. You know, it's not that much worse. What, on the other hand, happens if you have some crazy channel factory thing where like 10,000 people are sharing one UTXO? If you have a fuck-up where, you know, the person who ultimately arranged 10,000 people in one UTXO just disappears, you might be in a position where 10,000 times more data needs to go on chain for people to get their money back. Well, Bitcoin block size is limited. I mean, block sizes of all these systems are limited. There's bandwidth limitations. You just have to live with that. And it might be that we walk ourselves into a case where by trying to scale Bitcoin better, the failure modes get much worse. You know, if everyone uses channel factories and we have like 1 billion people on one output, those 1 billion people are not going to get their money back. And that may be good enough for an L2 if we're willing to not have unilateral withdrawal and just say, well, if it goes wrong, everyone's going to be really sad, including the guy who made it go wrong. But, you know, this isn't necessarily a very good outcome. And having multiple of these systems, well, they interact too, because block space is a market. So, I'm not sure that like rushing into these fancy L2 systems is actually a good idea. Like, we've never actually seen Lightning fail in a big way. A wallet the size of Phoenix has never failed at once. We've never seen a couple thousand channels get closed in a very short period of time. Ideally, we would understand better how this actually works, but currently Lightning just isn't at that point yet. So, the path forward. What should Bitcoin do? What covenant should we go and do? Are you going to wear an op-cat hat or a op-sig-hash any prevout hat? Hopefully not this one, because that's kind of a long thing to put on a hat. So, obviously op-cat wins that one. But really, you got a lot of different choices. And from technical point of view, it's interesting that sig-hash any prevout stuff, there seems to be a lot of consensus it's probably a good idea and probably doesn't have downsides. CTV is, like I mentioned before, a very simple opcode, and what it does seems to be relatively limited. You get all these like fancy tree manipulation magic opcodes, but they're ultimately things that are being proposed for specific use cases. And I'll go on in a second with a bit more tech detail on why this may not be necessary. But they have this political problem of just someone's got to champion a very specific use case. Now, opcat is interesting because once you have concatenation, you can build all kinds of stuff, including zero-knowledge proofs, allegedly. There's people who claim that they can do efficient, secure zero-knowledge proofs. I don't have the math background to be sure they work. In fact, no one does. But people are trying to do this stuff. And there's an interesting proposal out there that basically is to revive all the old script opcodes. Now, if you know about Bitcoin's history, you may know that Satoshi initially had a lot more opcodes in Bitcoin script than we currently have. Things like opcat, things like opxor, and so on. Well, opcat originally had no size limits. So you could just concatenate data together and over again to use up all your memory. And I think when Satoshi noticed this, Satoshi panicked and pulled out opcat and a whole bunch of other opcodes. But certainly if you added proper limitations, there's no reason why you couldn't have an opcat from a purely technical point of view. So in a way, you could imagine creating a script revival that restores Satoshi's vision. And maybe this will come through. And there's people working on this. Like the most recent one, I can't remember who was. Whatever Bitcoin Core developer was from Australia. I forget the heck of his name, but he's got a whole proposal on this. And of course, finally, you don't have to do anything. Like I said before, Lightning scales, I think, a lot better than people realize. And the world is smaller than I think some Bitcoin maximalists think. If there's only 4 billion people on the planet with smartphones, and you can have probably 500 million Lightning channels, maybe we don't actually need to rush into any of this stuff. But we'll see. So, let's get into a little bit of tech detail to figure out, where should we go next? And I haven't actually mentioned op check sig from stack, but basically the opcode does what the name suggests. It takes a signature and checks it against data on the stack. Now, the interesting thing about this is you can use this to do opctv. Well, how do you do this? Well, you can basically have a predefined digest, check a signature against that digest, fail if that signature fails, duplicate the signature, and then run checksig again. So what you're really doing there is you're taking data on the stack, to be exact, a hash on the stack, checking that a signature against it's valid, and then rechecking the same signature against the transaction that's spending the output. Well, why does this work? Well, because if this is fixed, you know exactly what the signed data must be. So this is actually equivalent to check template verify, which just checks the spending transaction directly. And that's kind of interesting. Like, you have one opcode that's actually has equivalent implications to another. But, that might seem a little esoteric. Let's go look at opcat. So, how do you actually use opcat? I mean, like, why do you have this thing? Well, an interesting thing is, first of all, opcat certainly enables covenants, but as my previous example showed, opcat is not actually necessary to implement CTV. Because the reason why you want to have opcat is you have a covenant where you want to do more than just predefine the spending transaction. You want to have some logic to it. A good example of this could be, well, imagine you have something like ARC, but you want the ability to go and withdraw early. Right? Let's suppose there's some way of proving that a certain number of people under some branch have in fact sold their coins. If you can go prove that, maybe that branch can be sold early, and you solve some of the liquidity problem by getting some of the money back earlier. Well, if you're going to do something like that, you're going to probably have some system where you build up a transaction in pieces and then constrain certain parts of the transaction. I mean, another way you could go do something like this is, what if you want to go have something like a channel factory, you want to add a new channel to it, right? You want to go put money into it. Well, again, you could imagine building up a transaction where the amount in the next transaction is whatever the amount is in the previous one plus a certain amount, plus a certain amount of Satoshis. If you can build up the transaction in pieces, you can go do something like that. In my example, like, this is very, I'm not showing the full extent even close to what you would do, but this is kind of like what it would look like. Build up the serialized data of the transaction, hash it, do check sig from stack again, verify, and then run that covenant check. And I'll point out, what's interesting about this is any opcat usage that builds up the transaction you're spending on stack is more efficient than you would think. In fact, it's quite a bit more efficient if all the data of the spending transaction is non-witness data. Why? Well, because of the witness discount. And I'll point out, you guys actually get to go learn about this insight first. I don't think this has actually been published anywhere because no one's gone into the level of detail to actually work out how this works. But basically, because of witness discount, it costs 25%, costs like 1/4 the amount of non-witness data. If you have a covenant that's checking a transaction that's not witness data, which is how it usually works, your extra cost to use opcat is roughly 25% more. It's not as much money as you'd expect for something that's literally building up the transaction on the stack. So, opcat's better than you would expect. Which also then means that, when you're talking about like fancy tree manipulation opcodes, maybe they're not actually worth it because they don't even provide much of an efficiency gain. And finally, opcat and CTV. So, I had this whole list of like what we should do next, but the interesting thing about it is a lot of these things are synergistic. If you have an opcat opcode, in reality, opCTV is probably what you want to actually use it. Because the way you use opcat is to build up a transaction on the stack, hash it, and then verify that the spending transaction matches what you want. Well, that's exactly what CTV does. So I would make the argument, if you're ever going to implement opcat, you actually should have opCTV anyway. And of course, you make the converse argument, why don't we just do this first? This is the simple thing. Opcat, it's a whole witch's brew, possible things could do. So CTV, definitely there's an argument it makes sense. But, how this politics will play out is hard to predict. This is one of the reasons why I'm writing this big paper on this stuff. And finally, this is another insight that you guys get to go learn about first that I don't think anyone's written about, which is fancy L2 systems are shared databases. And what do I mean by shared database? Well, if all of us in this room are sharing one UTXO, as the system state changes, we need to learn how the state of the system changed. And this is one of those reasons why roll-ups kind of seem to fail. Because in a roll-up, the system states could potentially change in a way that other people don't know about. They don't have that data. So what's a concrete example of this? Well, in ARC, the system, a way to talk about system state is say that once that initial ARC-UTXO starts getting spent, the thing you need to get mined to get your money back is changing subtly. All right? It's not just all these transactions, it's actually the output going down. Now in ARC almost doesn't have this problem because the set of data you need to publish to the chain is roughly the same every time. There's just minor technical details. But if you have an ARC where you can add money to a round after the fact, you definitely need to have a shared database of some kind with all the other users. Well, how does this play with the idea of proof of publication? So, what is proof of publication? Well, it's this idea that I came up with many, many years ago, which is a way of talking about what blockchains are. Because a blockchain is really a way of ensuring that data about a thing, such as transactions, is widely published. Well, why is that useful? Because to prevent a double spend, you ensure that everyone who might want to spend those coins has the set of all transactions spending them. All right? To spend a coin, I prove that my signature is published in a place where everyone can see that prevents the transaction from being spent again. In the case of L2 systems, the proof of publication aspect is saying, if I do something with the coins, I have to publish enough data to let you take action. And Lightning uses this, because in Lightning, if I want to close a channel, I must publish my channel. I must publish that closed transaction, and then you can go see it in the blockchain, and then you can go and take action. All right? There's no way for me to close a channel without giving you the opportunity to learn I've done this. HTLCs are another example. If I want to redeem an HTLC that's in flight, I have to publish this digest to the chain. Well, because I publish this digest to the chain, the next guy in the HTLC path, they can see that digest in the chain, and then they can go make use of it too. That's a very powerful concept. You know, I am forced to publish the data that lets my counterparty go do something. Now, what's interesting here is scaling. Any L2 system, if there's some kind of shared data structure, because of comp size, love of trees, we're going to put the data in a tree. And if we're going to put the data in a tree and we want the Bitcoin chain to be able to do something with it, well, we got to hash that data. So we have a Merkle tree. It might be a Merkle sum tree, it might be some other type of tree, but whatever it is, it's going to be a tree and it's going to be hashed. Well, how do trees scale? Log 2n. Like everything. So any of these systems, no matter how complex your L2 is, taking actions unilaterally is probably going to have roughly log 2 scaling. And in clever ones like ARC, if everyone has to take an action unilaterally, it'll have something like 2n scaling, right? Again, n being the number of outputs, number whatever, which isn't great, but isn't that bad. And it's just interesting that this actually seems to be where it all comes down to. And any system that tries to avoid this will end up being like something like rollups, which doesn't actually have the same security model. But with that, thank you. Do you want to do questions?
You know, you cannot totally replace like the full script with opcat. If you use ECDSA signature, but with Schnorr signature, you can add additional trick and reproduce the construction of the signature in the script. Yeah, you need like to green transaction a little bit, but you can use only opcat operator to receive like all data from the initial transaction, and additionally, yeah, for example, check some data and reproduce that the signature is like constructed the correct way. So probably, yeah, as we have implemented Schnorr signatures on Bitcoin, so we can upgrade the system only with opcat operator. So why we need like check a template verify opcode and additional ones?
Yeah, so I think the thing I would say there is like, so what check template verify is doing in this case is basically just providing a somewhat more efficient way of doing what the previous slide or this clever Schnorr thing works. In terms of what's possible, yes, it is true that, in fact, and I didn't mention it, but it is true that with fancy Schnorr crazy manipulation, you don't even actually need check sig from stack. You can actually do this with a check sig with a very carefully constructed signature. But CTV certainly does this in a cleaner, simpler way with lots of bytes of data. And since CTV itself is fairly small, if you're going to bother doing opcat, I think there's a very good argument that CTV makes sense, because a lot of these uses of opcat are just going to be that much smaller. It's not a huge difference, but given how simple CTV is, and I don't want to say that CTV doesn't have implications, but it's like everything opcat does has implications CTV does. So if you're going to do opcat, you might as well save a bit more bytes and also do CTV.
Am I correct that CTV verifies exact equivalence between the transaction and particular hash value? So it should be total equivalent. Or you can, for example, verify only the part of transaction data.
Yeah, so what I would say there is, you're correct in that here, let me answer this. So CTV, what it verifies is essentially the whole transaction, minus the bits where, you would create a hash loop, right? Obviously, you can't have in script A verify, construct in a way that verifies script B including the TX out hash, because that's dependent on script A. But what I would go say is that any construction with opcat, with something like check sig from stack or the clever Schnorr math tricks, you have to go and validate the whole transaction, because it just inevitably is that the thing that they are checking is the entire transaction. If I want to get technical, I'd point out it's entire transaction in the transaction signature serialization form, to get a bit technical there, but the key thing is you're verifying the transaction. And if you have an opcode that does this, you're just going to save some bytes and not have to create a dummy signature in certain cases. And in other cases where all you're doing is just predefining how a transaction can be split up, it just makes things easier. CTV for something like non-advanced ARC is certainly the way to go, because it's just less work to achieve the same goal. And finally, something I think I may not have mentioned explicitly is, everything I said about how opcat scales, of course, we're assuming that there aren't limits on opcat that are relevant. One way to implement opcat and fix the DOS attack would be to, for instance, have some kind of gas system where every byte you hash, adds to the transaction size. And of course, you choose limits that are restrictive. Yes, opcat, isn't necessarily the most efficient option. But if you choose limits that aren't likely to be hit, in quote unquote normal transactions, it certainly has this surprisingly cheap aspect to it.
Yeah, the main question just was probably in the future you can combine all particular hash types.
For example, single can pay or something like that with opcat, but if, for example, CTV covers all parts of the transaction, so probably you can be sure that only particular output exists in the transactions, and it doesn't make sense to you if, for example, other people add their outputs. And if you combine opcat with how it's called, single can pay, or yeah. So probably you can combine that with opcat, but if you're trying to combine that with check template verify, I'm not sure that it could work.
Well, I think a great example of that kind of problem, and something I didn't actually mention here was, CTV potentially has issues with out-of-band payments, because in practice, CTV is probably going to have to be used with anchor outputs, because CTV constrains the spending transaction so severely that the most reasonable thing to do is have it have zero fee, and then make miners and incentivize miners to mine it by having an anchor output that you then go spend with enough of a fee to pay for the parent. And once you have that, well, Now you can go save money by not actually doing that and just paying a miner at a band to go mine it. So, that's a potential issue. And I think the things you were talking about sig hash single and so on, well, there's other versions of like CTV you could imagine where, the thing isn't actually entirely constrained. Like maybe there's a way to add an output. But if you start envisioning this, you get the optx hash proposal. And optx hash is really complex. And it's very hard to wrap your head around what does it actually do. And my understanding from what I've seen from other devs is like no one's looked at it hard enough to be really convinced that it does what we want it to do. Whereas CTV, well, it's certainly not optimal. It's pretty clear what CTV does, and it's easy to be convinced. Now with opcat, if you have like an opcat with an opcheck sig with a special mode that checks the right things, you could certainly have a system where like maybe one signature would check one part, another signature would check another part. But the problem with that idea is a lot of these use cases, they don't actually need a signature to begin with. It's something like, something like ARC as an example. With ARC, it tends to be something as simple as, we just take this money and we split it up, and that's that. And there's really only one way you would go do it. So, I don't know. It's, this is why deciding on which covenant to do is hard, because there are just so many possibilities and so much nuance as to exactly how you use them. Like, I think if you're willing to go and kind of open the door to a very wide range of things, the fact that opcat is surprisingly cheap does make it quite attractive. It might not do everything perfectly, but, the fact it's roughly a 25% fee improvement in a lot of these 25% more fees in a lot of these common cases is surprising. And I certainly didn't realize that at first, but it's cheap enough it could do a bunch of interesting things. But if opcat enables zero knowledge proofs and people start implementing all kinds of crazy systems, maybe we're gonna introduce like Ethereum style MEV. We already have a little bit of that on Bitcoin due to ordinal auctions and stuff like that, which fortunately full RBF kind of fixes because anyone can bid and send the fees to miners. But, like if you open the door to anything, God knows what people are going to build with it. And I think, the Bitcoin community is already burned enough with all the shenanigans people have played with Taproot and the witness discount. So, as much as like I would say some of that's unwarranted, and Taproot wasn't really the cause of this. Politically, I think it's a lot easier to get check template verified through just because it's so simple and it's much more clear what it will actually enable. But we'll see.